In this video, we're going to talk about parametric equations. So we're going to start off with a few definitions. First definition, a plane curve is a curve generated by the equations x is equal to f of t and y is equal to g of t, where t is some number in the interval I. So we see an x and a y, and we know that curves or graphs are generated by these points x, y, but we're doing something a little differently here. Typically, we define x to be the independent variable, the y is the dependent that we generate from that x. We're actually now generating x and y from these two equations. Now this t here, this is the new input variable, this is a new independent variable. That variable t is called the parameter. The equations x is equal to f of t and y is equal to g of t, those are called the parametric equations. So what we are doing is we're incorporating a third variable now. When we look at some sort of a curve, we can measure it along the x-axis, we can measure it along the y-axis. It's completely true, right? We can see those pairings of x, y. We're going to see the same thing in our parametric equations. But what we're recognizing now is that x might itself be built off of another variable. And so there's a couple of good examples I'd like to give here. One is something you probably saw in your pre-calculus algebra class, in fact. When you were looking at quadratic equations, which is what we have here, when you're looking at quadratic equations or parabolas, we realize that these study motion, and they study motion affected by gravity, so a ball going up and coming back down, or a rocket ship maybe, whatever it might be, right? And a lot of times these equations were given to you in two different ways. The y always represented the height, that was consistent. But sometimes that x variable was given to you as an x, and it's called the horizontal distance. But sometimes, whether it's called x or sometimes it's even called t, is given to you as time. So somehow this height is affected by its horizontal distance, or we can measure the height based on how far it's been thrown horizontally, or we can measure it based on the time that's elapsed. And so really that horizontal distance is itself a function of time. If I throw a ball right now, depending on the trajectory and the force I give it and all of those sort of things, right, the time is going to be what occurs no matter what. If I were to throw the ball or not, time is going to continue to march forward. Now, if I throw that ball as time progresses, what I'm going to see is the distance from me that the ball travels is going to get further away, right? That ball is going to get further and further away horizontally. At the same time, that ball, if I do a good job, is hopefully going to go up into the air, and then at some point it will come back down. And so to simply say that the height is based off horizontal distance, that's not the whole picture. The height, horizontal distance are both based off of time. This is not the only example of this. This is, I think, one of the most visual examples I can give you. But another common example you may have seen in your algebra classes is profit, revenue, and cost. And so you may have been measuring profit, and so a lot of times this tends to move on a quadratic curve. It depends on the scenario, it depends on the workplace, right? But you might see that it works on a quadratic function, it might work on some other function. That's typically going to go up as you produce more items. I'll call it production, right? It goes up and then maybe it falls if we max out our production and we have to buy another warehouse. Maybe profit drops for a little bit. Maybe it'll go back up down the road. Right? I'm just kind of concentrating on these variables. We also sometimes tie this to cost. Profit, or we could even say instead of profit, we could tie it to revenue. But I like the profit cost a little bit better right now. A lot of times what we'll see is as the cost goes up, so does profit initially. And the reason for that is as you are buying more supplies, you're probably selling more things. So if I'm making, let's say, cars, and I sell one car, I'm going to have to pay the factory workers, I'm going to have to pay for the factory, I'm going to have to pay for the sheet metal, all that sort of stuff. So I have some costs, and this is probably a pretty significant chunk. But what happens if I sell 100 cars? I'm going to have a higher cost. I'm going to have to buy more tires, more parts, more everything. I might have to hire more people. That's going to go up and up. Profit, hopefully, is also going up too. Otherwise, I wouldn't be doing this. Otherwise, I'd be sticking with the one car. At some point, that might turn around and fall, right? It might be that now I have to buy a second factory, and that's going to cost me more money, right? That's the decision we've made. But the idea that cost is solely driving profit is not correct, but we definitely see that they move together. And they move together because of this variable production. That's kind of like the time, or what we could call the parameter t. The more things we produce, cost is going to go up. Hopefully, profit does as well. So with that in mind, Let's talk about how we're going to graph these planar curves. They're really not too complex. There's not a lot of new ideas in this because we're simply graphing x's and y's. The only difference is we're starting off with this third variable called the parameter t. And t is a parameter. It's not representing time in all cases. I do want to stress that. So for instance, the previous example, t was representing the number of cars, not time. So we want to select values of t on the given interval. And a lot of times these parametric equations will have given intervals. For instance, I can't produce negative cars. So the interval for cars might be from 0 to infinity. Or, maybe when I throw that ball, it's going to be in the air from 0 seconds to 15 seconds. At 16 seconds, it's not going to start going through the center of the Earth. It's just going to stop. The model ends. So we're going to have endpoints or intervals for our parametric equations. From there, we're going to compute the values of x and y for each t, just by using those parametric equations. And then finally, we're going to plot those points, the same way we've plotted points all our lives, and we're going to connect those points with these smooth curves. But here's another difference, including direction. We're indicating direction. Now that we have this third variable, the parameter t, included, that t is what is counting us forward. It is what is moving us forward. And that doesn't matter if it's time or if it's production, right? Numbers produced. That is what's going to move the x variable to. So we're going to indicate that this is the direction that we're moving along the curve. Or it could be that this thing's kind of bending around, and so it might go one direction, then turn another direction, then turn back another direction. So we're going to have to see. We're going to have to plot the points. We're going to have to see. So let's take an example. We'll start easy. Let's graph the parametric equation t is equal to x is equal to t minus 1, y is equal to t squared, and this t is going to be between -2 and 2 inclusive. Let's plot this parametric equation. So I'm going to start off the same way we started off in 8th grade, or whenever you studied functions. You set up an xy table. Now the difference is we have this new variable t, so it's the txy table. But we're going to plot points, meaning we're going to choose values of t, we're going to plug those into the x and the y, we're going to see what we get. Now when I'm choosing t, I don't want to just choose randomly. I want to make sure I choose a good sample of numbers and a sample that's going to span my interval. So I definitely want to start at -2. That's the first number in my interval. I definitely want to end at 2. I wouldn't want to stop, say, at 0, because then I don't know where the function actually ends. I don't know where the graph actually ends. From here, I'm going to go ahead and just count up by ones. That seems to make sense to me. It gives me 5 points. That's a pretty good number of values to plot here. We've seen with quadratics that simply plotting 2 points is not enough. Simply plotting 3 points might not give us a full picture. So I would recommend with these parametric equations, always start with 5. If you want to add more on, if you want to add more later, that is fine. Do try to keep them in chronological order. Remember, these t's are counting up. It doesn't matter if it's time or production or whatever. There's an order to these t's, so we want to make sure we're going up on those. So now I'm just going to plug in. -2, plug into the x, -2 minus 1 is -3. Then I'll plug it into the y. -2 squared, 4. -1 minus 1, -2. -1 squared, 1. 0 minus 1, -1. 0 squared, 0. 1 minus 1 is 0. 1 squared is 1. 2 minus 1 is 1, and then 2 squared is 4. So we notice the y's repeat, and that kind of makes sense because it's quadratic. The x's didn't. That's linear, so those kind of both make sense. All right, let's do our graph. I'm not plotting the t. The t was allowing me to get to these values. It's showing me how I move. I'm plotting the x's and y's because we know that this is the x-axis, this is a y. I'm going to start with the next value of -3. And this I will always remind you is easier on graph paper, so I do my best to keep it pretty smooth, but I always recommend doing this on graph paper when you have it available. -3, 4 is our first point. -2, 1 is our second point. -1, 0 is our third point. Then we have 0, 1, and then we have 1, 4. 1, 2, 3, 4. And so now I'm going to connect my dots. And notice we get a quadratic. And we saw that there was this x squared here, so we kind of assumed that there's going to be some sort of parabolic shape at the very least involved, and we see that. Now, a couple of differences that we're doing here from what we've done in the past is typically you stick a pair of arrows on that and you say, all right, there's my graph. It goes on forever and ever. No, not here, right? Because we have the endpoints. We start at -2, we end at 2. We cannot exceed those points. We have to stop at those 2 points. So I need to erase these red lines. If my computer will switch over, there it goes. I need to erase those. I have firm endpoints on those points. The next thing that I need to indicate is the direction, because remember, that is key to these parametric equations. If you don't draw the direction on there, your graph's wrong. So think about the point we started with. We started with this point right here. That's the first one we had, right? From there, we moved to this next point. We moved on from there. So we are moving from left to right on this graph. Is that always going to happen? Absolutely not. Let's take a look at another example. Let's take x to be equal to negative sine t, y is equal to negative cosine t, and our t is between 0 and 2 pi. So already in our minds we're seeing some trig functions. 0 to 2 pi is a lot of times a full rotation of sine or cosine, not necessarily a full rotation of an ellipse or of a hyperbola. So we'll see how that plays into it, but we can understand why the t might be limited in such a fashion. We know that 0 to 2 pi gives us all the values for sine and cosine. Let's set up my x, y table. I'm going to start with obviously a t value of 0 because that's on the leftmost side of my interval. I'm going to end at 2 pi. I wouldn't want to count by ones here because I'd really like to be able to graph these values a little bit easier than that. So I'm going to count maybe by pi over 2's. Pi over 2, pi, 3 pi over 2, 2 pi. That gives me a total of 5 values. That seems to be a good minimum. If I need to, I can go back and add more. Maybe I want to count by pi over 4's. We can consider that, if we need to, if we don't see enough points to see what's going on. So I'm going to start by plugging my 0 in for sine. Sine of 0 is 0. Cosine of 0 is a 1, but then because there's a negative in front, we get a negative 1. Then we take the pi over 2. Sine of pi over 2 is 1, but because there's a negative in front, it's a negative 1. Then we move on to cosine of pi over 2, that's 0. Sine of pi is 0. Cosine of pi is negative 1. Make it a negative again, it turns into a positive. Sine of 3 pi over 2 is negative 1. Make that negative, it turns into 1. Cosine of 3 pi over 2 is 0. And then sine of 2 pi is 0. Cosine, we're back to the negative 1. Now you might be saying to me, well, 2 pi wasn't included, right? That 2 pi was not included, so why have I written this point down here? For the same reason we did it with piecewise functions, way back again in algebra. It is helpful to know where I'm getting to. So for instance, if this thing was spread out, it's not going to be, but let's say, we started, we'll put it at 0. Let's say we ended here at 2 pi, and it does something like this. Well, if I'd stop simply at 3 pi over 2, I'm going to exclude everything from here to that open dot, everything in there. So I'm going to go right up to that endpoint, and then all I'll do is indicate with an open circle. If I don't want it, I'll indicate that with an open circle. So I do always recommend use both the endpoints for your intervals. All right, now let's do the graph. I guess it doesn't matter if it's in green. 0, negative 1. That's our first point down there. Negative 1, 0. There's our second point. Apologies, my computer's really delayed here. Let's try that again. 0, negative 1. Negative 1, 0. 0, 1. And then 1, 0. And they should be all balanced around the origin. So this was our first point down here. And from there, we're moving this way around. That's going to be important in just a second. Then notice at the 2 pi, we get back to 0, negative 1. So we've completed the rotation. We've completed what is in fact a circle. So I don't want to connect these on straight line paths. I do know that sine and cosine do give me curves. So this will give me a circle. If I were to draw it as a diamond, that would be incorrect, right? And I actually drew in the exact opposite direction it actually goes. I want to put the arrows on there indicating the direction that it's traveling. And how do I know that? The first point on my list, the first t value, was this one right here. It came up here next, here next, here next, so forth. And so sometimes you can even label them if it helps as you're writing them down, so you can keep track of that order for second, third, fourth. And we can see how we're moving around that circle. Let us take one more. Let's take x to be the square root of t. y is equal to t minus 1. And this time, I'm not going to specify an interval. So intervals may be restricted. For instance, like I said, that baseball is going to leave at time 0. It's going to come back down to the ground and the scenario ends. It's not going to just keep going. But it could be something like our manufacturing problem where there's nothing stopping us from making more items, right? We can continue to buy more resources. We can continue to hire more staff. We can build more factories, and we can make more and more things. We might even be able to move into negatives in situations, right? Maybe we want to look at some sort of timeline based off of year 2000. Well, there's time before that. So there doesn't have to be an interval specified. Also, there might be natural restrictions to this interval. So here I look at this and I'll say, well, I don't know where to start because there's no interval. So that should mean that there's all values of t. But can I have all values of t? No, I can't, because if I'm going to take the square root of t, that means that t has to be greater than or equal to 0. So here, based on the parametric equations we're given, we have the built-in restriction that t has to start at 0. From here, I'm going to count up by ones. I'll go to 5 again. It seems like it's worked out so far. And I'm going to start plugging in. Square root of 0 is 0. 0 minus 1 is negative 1. Square root of 1 is 1. 1 minus 1 is 0. Square root of 2. I don't want to do it. I don't want an irrational number. So I realize, you know what? I don't like 2. I want to count only by perfect squares, because that way I'll have just nice whole numbers. I get to choose what I want to count by. There's no end to this interval, so I'm going to go 4, 9, 25. Square root of 4 is 2. 4 minus 1 is 3. Square root of 9 is 3. 9 minus 1 is 8. Square root of 25, 5. I skipped 16 for no reason at all. Maybe I'll throw 16 in there just because it'll give me a little smaller number. So 4, and then 16 minus 1 is 15. Could I have used the 25? Absolutely. Nothing stopping me from doing that. All right. So the first point we have is 0, negative 1. From there, we go to 1, 0. Then we go to 2, 3. Then we go to 3, 3, 4, 5, 6, 7, 8. So way up here. And so what I can already see, the next point is going to be even higher, right? It's going to be way up here somewhere. I can see that I'm getting a curve. We started off relatively small growth, getting steeper and steeper, and this time it's, continuing to progress. So now I need to figure out what I'm going to do with this end. The first example we did, I didn't mean to erase that, but I put a firm endpoint on that. And I don't want to do that here because it does continue. Remember, there's nothing stopping this interval from growing. So I'm going to put an arrow on the end to indicate that it continues out. I'm going to throw a couple other arrows on this just to indicate that the direction does go from left to right. We knew that based on the direction we're graphing. I will also point out that sometimes if we have an infinite direction on both ends, let's say we have a parabolic shape again, but this time the interval is going from negative infinity to infinity. If the direction is, say, moving from left to right, if I stick arrows on like this, that is incorrect. That is indicating the left is actually going to the left. So if I want to indicate that it's going from left to right, what I'm going to do is I'm going to put an arrow on the end, but I'm going to have it facing the opposite direction. It's going to go from left to right and everywhere in between. So the arrows on the end are indicating it continues. It doesn't just end. That's what the dots do. They end it. But then I want to have the arrows in between to indicate that continuation too. All right, next thing I want to do with these things is I want to convert from this parametric form to rectangular form. I want to have a y in terms of x. That is useful. Sometimes we need to be able to have that equation where we don't care about how the t's are affecting it. We don't want to see that equation. We just want to see how the x's and y's are tied together. And so to do this, as a general rule, what we're going to do is we're going to solve for t in one of the two parametric equations. We're going to plug it into the other. So to convert from parametric to rectangular form, solve for t and replace, I'll say solve for t in one of the parametric equations and replace in the other. Now, I said this was a general rule. There's going to be a couple cases this is not going to work. So most of the time, right? Go ahead and make a note. This is most of the time. If we have trig, we might do something else. In fact, we will do something else. And we'll see examples of that in just a few minutes. Okay. All right, so I want to come back to this first example we did. We already know what the graph should look like. I want to take these two equations and I want to convert to rectangular form. I did not specify which equation you need to solve for t, and generally what I'd say is take the easier one. Now with the stipulation, or the, I guess, caveat there too, that if there is not an easier one, it's generally easier to solve for the one with the x, because then we can get y as a function on x. Notice this will be a function, y is a function on x. In this case, it is a function. If it was not a function, or if x was a function on y, then maybe we would want to solve for the t in the y equation. But generally, if equations are equal, let's go for the x equation. In this case, the x is the easier one. We don't want to take the square root of both sides because that's going to give us plus and minus. So I'm going to take that x equation and I'm going to solve for dt. So that means I'm going to take the 1 and add it over. T is equal to x plus 1. And so now I'm going to take the y equation and simply plug it in. X plus 1 squared. And there we have a rectangular equation. We have just x's and y's, and that's the goal of rectangular. Remember, rectangular is just x's and y's. We have our y as our independent, the x is the dependent here in this format. Let's compare that to the graph that we have. X plus 1 would be a quadratic shifted to the left by 1. That's exactly what we see, with the exception that we have some firm endpoints on here. So if I were to just box this right now, call it a day, I'm wrong. And the reason for that is that these parametric equations have interval endpoints. So we have got to find this. We've got to figure out where those endpoints are. We know where they are for the t. T was between -2 and 2. What I need to do is I need to figure out where they are for the x. And so in this example, we've already done that, right? Because we set up the table. We know that it ends at -3 and 1. The x is -3 and 1. So I'm going to add to this. The x has to be between -3 and 1. Now I have a complete answer. I have y as a function on x. We have the x's are limited. So now if I were to do this graph, I'd be saying, well, I have a quadratic that's shifted to the left by 1. But I can't exceed -3 and I can't exceed 1. And so we draw it with those endpoints and we'd have our graph. Do you need to also restrict the y's? Not if you have a function, right? When we're restricting these variables, we're restricting them in a way so that we won't get too much, right? We're not going to get extra. Here we had something that was a function, so we only need to restrict the x, because by restricting the x's, we also restrict the y. If we have something that looks, say, like this, let's call it 1, and we'll say the y's go from -3 to 3. Well, now we'd actually have to restrict it according to the y's, because simply going from 0 to 1 on the x, we don't know what the y's are doing. So it depends on which way it's a function. You can always restrict it on both if it makes you feel better, but we need to restrict it on the direction that it's going, or the limiting factor. Let's move on to that second one, because this was the trig equation, and that was the one I gave the caveat that we're not just going to solve for t. Let's see what happens if we try to solve for t. So I'm going to take that x variable and I'm going to solve for t. So I have x is equal to negative sine t. So I divide by the negative. If I want to get t by itself, I'd have to take the inverse sine. And so that would be my t variable, my parameter. I'd take that, I'd plug it into the cosine. Cosine, we had negative cosine t. So we'd have y is equal to negative cosine of the inverse sine of negative x. And that is not wrong, but if I had you do that operation, had you get it to the rectangular form, and then asked you to graph this, you'd have no idea what the graph looks like. I have no idea what the graph looks like. We're not comfortable graphing cosines of inverse sines, right? And so that's why we're going to approach this one a little bit differently. Our goal is to get a rectangular form, one that we recognize how to graph. So let's think about something else we could do. Now this one's kind of a giveaway because we've already looked at the picture. We know that it's a circle. Kind of know that what circles equations are supposed to look like. But what I recognize is that I have two equations here. I can always add, subtract, multiply, divide two equations. That gives me a new equation that is still a true equation. So if I wanted to take the x and the y, add them together, I'd have x plus y is equal to negative sine minus cosine. That would be another true equation. It's not a really useful one, but it's a true one. I'm trying to get rid of the t's. That is my goal with converting from parametric to rectangular. I'm trying to get rid of the t's. If I had a sine squared plus a cosine squared, that would disappear. The t's would go away. So what I'm going to do here on the trigs is I'm looking for a way that I can get to a Pythagorean identity to get rid of those trig functions. I'm going to square. I squared my left-hand side, I get an x squared. I square my right-hand side, negative sine squared is positive sine squared t. I square my y, that's y squared. I square the negative cosine, that's cosine squared t. And now I'm going to take those two equations, add them together, so I get x squared plus y squared equals sine squared y t, should be a t, plus cosine squared t. And sine plus cosine squared, just as we said a second ago, 1. So here is our rectangular form. That is, of course, a circle. We know that circle would have a radius of 1. We know that its center is at 0, 0. If we wanted to list the domain and the range, the domain would go from negative 1 to 1. And the range, same exact story, negative 1 to 1. I'm going to skip past that third one because I do want to take a couple that we haven't seen so we understand how we can put those together too. I'm going to do another one with the square root, a little bit different problem. So let's take the square root of t plus 2 as our x. Y is equal to the square root of t minus 2. And I want to convert to rectangular form. So this is an example where they're looking very even to me. One is not easier or harder than the other to solve. So I'm going to start with the x. I'm going to take the x and I'm going to solve for the t. So I subtract my 2 over, and so I get the square root of t is equal to x minus 2. And if I wanted to get t all by itself, I could go ahead and square both sides, and that's exactly right. Then I could plug that into my equation for y. But what I actually notice, over here in this y equation, we have the square root of t. Right here we had an equation for the square root of t. I could write at this point, if I wanted to, write it as y is equal to x minus 2 minus 2. That is a completely valid statement. I've replaced an equivalent variable. The variable wasn't simply t, as the square root of t. Now if I'd wanted to, I could have also written that as y is equal to the square root of what t was, which is x minus 2, I should have had a squared on it, x minus 2 squared minus 2. And if we take the square root of a squared, we're just left with x minus 2 again. So any which way we do this, we're going to get the equation y is equal to x minus 4. Now, I might think I get to just box this and call it a day again, but we need to consider our restrictions. We look at this and we say, hey, there's no restriction on t. Great, done. But remember, there might be natural restrictions. These equations have built-in restrictions on t. That t is not allowed to be less than 0, because if it is, we get a negative under the square root. So our t has to be greater than or equal to 0. That means the x, the smallest it can possibly be, is 2. If t is equal to 0, x is equal to 2. If t is equal to 1, then we get x is equal to 3. And those values are going to grow and grow and grow. And you can test that through again in the table. So what I need to come down here and state is that x has to be greater than or equal to 2. Let's say I wanted to do the graph from here. The graph from here is relatively simple. It's just a linear equation with a y-intercept of 4, a slope of 1. It's going to go up 1 over 1 from there. So we draw this line. This would be 100% wrong because we're indicating the direction is going both ways away from it. We've also not taken into consideration our x being 2 or greater. And so what I need to think about is the points that satisfy that domain. So yes, we have a y-intercept of -4 for this line, excluding the domain. We go up 1 over 1. We go up 1 over 1 to get to, apologies, to get to 2, -2. We go up another one and over another one to get to 3, -1. Well, it starts at 2, so we're not going to start at the y-intercept. We're going to start at this point right here, and that's going to be how we move forward. We could have also done this graph through just plotting some points. We could have taken the first value, 2. 2 minus 4 is -2. 1 minus 4, sorry, not 1. 3 minus 4 is -1. That's that point right there. 4 minus 4 is 0. That'd be that point right there. And so this would be the line that we get. We need to indicate direction on it as well. I stuck that arrow on there without a whole lot of thought. I do know that it's moving from left to right. And so I'm going to put a couple arrows on there just to indicate that is a consistent direction. I do like to see a few arrows on these parametric curves because there is a chance that it could turn around. It could be coming in one direction from one way, and then it could all of a sudden kind of flip around to coming in from the other direction. So we got to be careful of that. We need to be aware of the direction can change. Let's take one last example. Let's do x is equal to 2 plus 4 cosine x. Sorry, cosine t. X is equal to 2 plus 4 cosine t. Y is equal to -1 plus 3 sine t. And our t is between 0 and pi. So once again, we have a trig equation. And so I need to think about, well, what can I do to get rid of these trig functions? I'm shooting to get to one of my Pythagorean identities. Now before, the first thing we did, and I should write my instructions here, we're going to convert to rectangular. The first thing that we did was to just go ahead and square so we could get the sine squares and cosine squareds. If I were to square right now, I'd get x squared is equal to 4 plus 16 cosine t plus 6, that should be an, that's right, 16 cosine t plus 16 cosine squared t. And that's giving me a squared term, but it's also giving me a cosine term, and that's not real helpful. So what I'm going to do first is I'm going to isolate the trig functions. So I'm going to subtract 2, then I'm going to divide by 4. So cosine squared t is equal to x minus 2 over 4. Same thing on the y, I'm going to add the 1 over, and then I'm going to divide by 3. So sine t is equal to y plus 1 over 3, like so. I don't need to square it on the cosine yet. I'm getting ahead of myself. So I've isolated the cosine and I've isolated the sine. Now that I've isolated those, I want to be able to add them to get that sine squared plus cosine squared, which does mean that we need the squares. So now I'm going to square both sides. I'm going to have cosine squared t is equal to x minus 2 over 4 squared plus sine squared t is equal to y plus 1 over 3 squared. Now that I have those squares, let's see what happens when we add them. So we have cosine squared t plus sine squared t, adding the two equations, equals x minus 2 over 4 squared plus y plus 1 over -3, that should have been a positive 3, I just can't read my writing, over 3 squared, and we get a 1. The parameter, the variable t has disappeared as we wanted. That has all just become a 1. And I've also gone ahead and moved the square to both top and bottom, because if it wasn't obvious at this point, it should be now. What we have here is an ellipse. We have an ellipse that's centered at 2, -1. The x spans 4 units either side, the y spans 3 units either side. Now, I might think I can just end it here, but again, we have to consider the interval. Before we had from 0 to 2 pi, that was on the circle we had with the sine and the cosine before, we had the 0 to 2 pi. Here we only have from 0 to pi, and so there's a good chance we didn't get the full spectrum of values. So I'm actually, even though we have the rectangular form now, we could we know what this thing would look like. Like I said, it's going to go to the right by 2, going to go down by 1. That would be our center. From here, 4 units left and right. Those would be our edges. And then 3 units up and down. 1, 2, 3. 1, 2, 3. We know that this would be the full ellipse, but the problem is I think there's a good chance I didn't get that full ellipse because of this restriction, the parameter restriction. So even though we weren't asked to do the graph, even if I'm just asked to write the equation, I've got to figure out where those x's and y's are ending. I've got to figure out if I'm only getting part of my ellipse. So I'm going to set up a txy table. So if I plug in 0, cosine of 0 is 1, so we have 4 plus 2, that gives me 6. Then we plug in the 0 for the y. Sine of 0 is 0, so we get the negative 1. That's our first point. Let's compare to our picture. Our first point, negative 6, 1. No, it's positive 6, excuse me. Positive 6, negative 1. That's this point right here. I'm trying to switch colors. It's not doing it, though. I'll just put a little first beside it. That's our first point right there. Let's see where we go from here. Next, we're going to plug in, say, pi over 2. Now it switches. Pi over 2. So if I plug pi over 2 into the cosine of pi over 2 is 0, so we get just a 2. And then sine of pi over 2, that is equal to 1, so we'd have 3 times 1, which is 3, minus 1, that gives us 2. So we get the point 2, 2, and we should see that that would be the halfway point right here, so this is our second point. And then we'll finish up with the end of the t interval, which is the pi. Cosine of pi is negative 1, that would give us negative 4, plus 2 is negative 2. Sine of pi is 0, add the negative 1, we get negative 1, so negative 2, 1 would be this point right here. This would be the third point that we have. So what we see is we're not actually getting that bottom half of the circle, we are only getting the top half of the circle. So I want to make sure when I draw this, I'm only drawing half of, I say the circle, the ellipse. Should be a curve. It is an ellipse. We are going from right to left. That would be the direction that the ellipse is traveling. We have only half of it. And so now, if I'm going to restrict this thing, I can say that x restrictions between negative 2 and 2. Not negative 2 and 2, negative 2 and 6. Should be a 6. And that's not wrong, but I knew that this ellipse was only ever going to be from negative 2 to 6, just based on its properties, right? I need to restrict the y on this one to be able to give my accurate representation of my graph, and so my y is going to go from negative 1 up to 2. So now that I have that y restriction in there, now I have the complete graph. If I don't give really the y, if I don't give this bottom piece down here, then I haven't given an accurate representation of what the parametric equation was representing. One last idea I'll leave you with. We've now looked at how to graph these parametric equations, and we've looked at how to convert from parametric to rectangular. What if I were to go the other direction? Let's say I were to take a rectangular equation, let's say 2x plus 1, and I wanted to go convert to parametric. Well, the reason I'm going to spend all of 1 minute on this is because it's super easy. If I'm given no guidance on this, one way I could do it is simply say, well, let's let x equal t, in which case y is equal to 2t plus 1. Just saying if x is t, then I get 2t plus 1. Or I could say let's let x equal t plus 1, in which case y is equal to 2t plus 1, just substituting that x right in. Of course, I could simplify that to 2t plus 3. I could do this all day long. I could make it a little bit trickier if I wanted to. I could say, x is equal to t squared, and then we could replace that. But then we have to start also thinking about, well, am I creating restrictions? So for instance, if I were to say, let's let x equal to the square root of t, we could write y is equal to the 2 square roots of t plus 1. I wouldn't want to do this because that's creating an unnecessary restriction, a restriction that's not supposed to be there. It doesn't give me the full line anymore, so that's not good. So I'd absolutely stick with the easiest form. There will also be times that there are built-in restrictions, and so this will be a little bit different, right? For whatever reason, we want our t to start out at, our x rather, to start at t plus 5. whatever the reason is. And so we just plug that in, t plus 5 plus 1, and we get 2t plus 11, right? We get an x and y. It's still not hard, but there may be times that we are told what to start with, and that's because, again, with the baseball problem, maybe we're viewing time as starting 2 seconds after we throw the ball because we want to see the progression from that point. Or maybe we're going to measure what happens up to the point the ball is thrown. We're going to measure its path there, or whatever the scenario is. So there might be reasons we change that x from being simply t. But that will be given, or it will be something that we're able to calculate.